Assalamualaikum and good day everyone. Today we would like to present our laboratory experiment for BLK 246 thermodynamic and heat transfer. The title of our experiment is Force Convection heat transfer. My name is Muhammad Zaman Himi bin Zulkifli. My metric number B112410227. These are our group members who were involved in conducting the experiment, collecting the data and preparing the report and presentation. Introduction. This experiment focuses on force convection heat transfer. The main objective is to study the temperature distribution along pin and fin heat transfer surface under free and forced convection conditions. By using a flow and different heat transfer surface, we can observe how heat transfer become more effective. This experiment also helps us understand the application of convection in engineering system and cooling system. Procedure. First, the pin heat transfer surface was installed into the setup. Then, the heater was turned on and left until the temperature became stable. Next, the temperature probe was inserted into each measuring point one by one, and all temperature readings were recorded. After that, the fan was switched on to create force convection airflow, and the same measurement process was repeated. Finally, the pin surface was replaced with the fin surface, and all the steps were repeated to compare the result. Work process. At the beginning of the experiment, the main power supply was insulated and both the heater and fan control were set to minimum for safety purpose. The pin heat transfer surface was installed securely and the heater power was adjusted to 30 watts. The system was allowed to stabilize for around 10 minutes. During the free convection process, thermal paste was applied to the probe before taking temperature measurement from hole 1 until hole 6. A sliding magnetic cover was used to prevent a stray airflow from affecting the readings after the temperature became stable, and all readings were recorded carefully.
So yang pertama sekali kita akan on dulu switch di belakang. Kemudian kita akan pasang fan apa? Fan je. Kita akan pasang fan dekat atas dia punya, itulah kat atas tu. Kemudian kita setting, kita pada on apa semua tu, kita setting ni, kita on. Dan kita setting power dia kepada 30 watt. Slow dia 3 milisecond. Kita buat kepada 3.1 milisecond. Kat sini juga kita akan dapat lihat dia punya airflow, iaitu lubang pertama, satu. Lepas tu dia ada lagi beberapa lubang kat sini. T1 pada fan. Okey, untuk T1 adalah dia pergi kepada fan. Yang kedua, T2 ni dia akan pergi kepada pin surface. Dan yang T ketiga adalah dia punya probe untuk measure kita punya temperature.
Okay. Assalamualaikum. My name is Muhammad Farhan Adi Afiq bin Rosli. I'm from BELK S2/2. Now I want to talk about measurement table. Based on the measurement table, the experiment was conducted at a heat transfer surface power of 30 watt under free or forced convection condition. For position 1 until position 6, the probe temperature, surface temperature and inlet temperature were recorded. From the table, we can see that the probe temperature decreased as the distance increase. For example, in the first data set, the probe temperature decreased from 33.1 degree Celsius at position 1 to 28.5 degree Celsius at position 6. Meanwhile, the surface temperature remains relatively constant with only a small increase along the position. The inlet temperature also stay almost constant through the experiment. In addition, the temperature difference between the probe temperature and inlet temperature increase gradually from position 1 to position 6. This show that heat transfer become more significant at a larger distance from the starting point. For the second table, a similar trend can be observed where the probe temperature decrease while the temperature difference increase. Overall, the results show the relationship between temperature distribution and heat transfer along the surface during convection. So next, we're going to delve into the thermal performance of different surface types, specifically focusing on how temperature difference correlate with position and power input. So the left chart, this graph illustrates the temperature difference in Celsius across 6 different positions on a pine surface. We observe a consistent increase in temperature difference as we move from position 1 to position 6. The temperature difference starts at approximately 1 Celsius at position 1 and rise to almost 6 Celsius by position 6. This suggests a heat distribution or accumulation pattern along the length of the pine surface. So the right chart, here we can see the same analysis for a fine surface. Similar to the pine surface, there is a clear trend of increasing temperature difference from position 1 to position 6. However, the overall temperature difference are notably higher from the fine surface. It begins around 2.8 Celsius at position 1 and reach around 7.4 Celsius at position 6. This indicates that under similar conditions, the fine surface experience greater temperature variation across its prone position compared to the pine surface. So next, temperature difference versus power for pine surface. This chart investigates the relationship between temperature difference in Celsius and applied power in watt for the pine surface. As expected, increasing the power input leads to a general increase in temperature difference. The data point generally follow an upward trend, indicating that more power results in higher temperature difference. The trend line with the equation y equals 1.76955 x plus 3.0182 suggests a relative linear relationship between power and temperature difference for this pine surface. For example, at 30 watt, the temperature difference is 12.4 Celsius and it reached to 26.7 Celsius at 50 watt. Both pine and fine surface show an increase in temperature difference across prone position, with fine surface exhibiting higher overall difference. For the pine surface, there is a strong, nearly linear correlation between applied power and the resulting temperature difference. These findings are crucial for understanding the thermal behavior of this surface and optimizing their design for heat dissipation or retention depending on the application. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Faiz bin Amiruddin and I will presenting about the discussion part. And my metric number is B1124100170. Okay, the first question. The extended surface is made of stainless steel, which is relatively poor conductor. How will using aluminium or copper, better conductor, affect the temperature gradient and the overall efficiency? Okay, replacing stainless steel with aluminium or copper enhances heat transfer due to their higher thermal conductivity. Thermal energy moves more effortlessly through the fin, minimizing the temperature decline from its base to the tip. Consequently, the temperature distribution across the surface becomes more uniform. This allows the fin to dissipate more heat into the ambient air, raising the overall efficiency. Copper delivers peak thermal performance, whereas aluminum offers a highly efficient, lightweight, and cost-effective alternative. Next question. Explain the effect of airflow in force convection. Give one example for the application. The answer: airflow accelerates heat transfer in force convection by constantly circulating air across a heated surface. Increased air velocity dissipates heat rapidly, leading to quicker cooling than natural convection. Essentially, faster airflow directly boosts heat transfer efficiency. A typical example is a computer's cooling fan, which forces air over a heat sink to draw heat away from the processor. Okay, next is discipline. Strict adherence to operational guidelines ensure the safe and responsible execution of the laboratory activity. Prior to swapping any heat transfer surfaces, the main electrical supply was deactivated and both heater and fan controls were adjusted to their minimum thresholds. Rigorous experimental techniques were maintained throughout the session, including the application of thermal paste to the surface probe and the deployment of the sliding magnetic cover to isolate active test holes for the data accuracy. Team members collaborated productivity to produce productively to document temperature distribution data, maintain an orderly workspace, and preserve equipment integrity. Finally, collective discipline was demonstrated through the synthesis of these findings into a structured report and a multimedia presentation, ensuring successful submission to both the Ulearn platform and the designated YouTube channel ahead of the week's deadline. Okay, last but not least is conclusion. In summary, this experiment successfully validated the fundamental mechanics of free and forced convection heat transfer across extended surfaces. The result confirmed that forced convection substantially increases heat transfer rates relative to free convection as the induced airflow thins the thermal boundary layer and elevates the convective heat transfer coefficient. Regarding the geometrics evaluated under forced convection, the pin surface induces greater turbulence, resulting in a more pronounced temperature gradient and accelerated localized heat dissipation at the base. Conversely, the fin geometry facilitated a more uniform and gradual thermal distribution across its entire span. Ultimately, the experimental objectives were fully met, establishing that surface geometry and fluid velocity are vital parameters in optimizing convective heat transfer performance for engineering system. That's all from us. Thank you.